Hello students, in this video we are going to discuss the analysis of cannabis sativa and its products. Cannabis sativa, also known as hemp, is a species of Cannabinaceae family of the plants. It is most widely used illegal drug in the world. Other names are grass, pot, weed, tea, Mary, Jane, daga, etc. The cannabis, more commonly called as marijuana, refers to the several varieties of cannabis sativa or Indian hemp plant that contains the psychoactive drug delta-9 tetrahydrocannabinol or THC, which is believed to be responsible for the most of the characteristic psychoactive effects of cannabis. This leads to the high that is experienced when cannabis is consumed, and this delta-9 THC is rapidly converted to its active form 11-hydroxy delta-9 THC. This is the structure of the most potent compound present in cannabis sativa, that is delta-9 tetrahydrocannabinol or delta-9 THC. The compounds which have a structure similar to THC are known as cannabinoids. This cannabis sativa is a dioecious plant, and the female plants are preferred because they produce more of the glandular trichomes and are richer in cannabinoids. The flowering tops of cannabis sativa has highest THC concentration. The marijuana, which contain about 0.5 to 10% of delta-9 THC, is prepared from dried flowering tops and the leaves of plant. The hashish or hash or charas, it contains about 5 to 8% of THC. The hash oil contain about 15 to 30% of THC concentration. The ganja are the buds and the flowering tops of the female plants, and the bhang is cut and dried large leaves and the stems of the plants. The dried leaves and the flowers of the cannabis plants are known as marijuana, which can be smoked, consumed in an edible form as cookies, brownies, gummies, etc. The effects experienced by marijuana or cannabis user are variable, and it will depend upon the dose, method of administration, any prior experience, any concurrent drug use, personal expectations, mood state, and social environment in which the drug is used. People who use large quantities of cannabis may become sedated or disoriented and may experience toxic psychosis. The toxic psychosis is a state in which a person is not knowing who they are, where they are, or what time it is. The high doses of this cannabis also cause fluctuating emotions, fragmentary thoughts, paranoia, panic attacks, hallucinations, and feelings of unreality. An altered state of consciousness. The user may feel high, very happy, euphoric, relaxed, sociable, and uninhibited. The effects of inhaled cannabis are felt within minutes, reach their peak in 10 to 30 minutes, and can last up to 12 hours. These cannabis sativa plants can be obtained from different sources. It is originated from different regions of the world, and the plant material can be used as a herbal material once dried. The low quality products which contain stalks, seeds, leaves, and flowering tops may be compressed into blocks. It may occur as a loose herbal material, or it may be rolled into corn mob, wrapped in vegetable fibers, etc. The higher quality materials, composed of fruiting tops and the flowers alone, they may be also encountered. If tied around a bamboo sticks, this material is known as Buddha sticks or Thai sticks. A central bamboo cane is used around which up to 2 grams of herbal material can be tied. The material can be seized in bundles of up to 20 sticks. An African equivalent is to wrap the material in a small roll of brown paper, and such rolls frequently contain less than 0.5 gram of cannabis per roll. The cannabis products are administered in a number of different ways. The most common method involves mixing with tobacco and smoking. A typical hand-rolled joint contains approximately 100 milligrams of resin or 260 milligrams of herbal material. Although the amount used will depend upon the strength of material and the requirements of the user. Alternatively, a drink known as bhang may be made from the material, or special foodstuffs can be prepared into which cannabis products have been incorporated. Prior to the process of identifying whether or not a material contains cannabis or its products, a decision must be made whether the sample is a bulk sample or a trace sample. A bulk sample can be defined as anything that can be seen, while a trace sample in terms of cannabis can be loosely defined as one which would easily be contaminated. Their analysis follows the sequence: physical description, presumptive tests, thin layer chromatography, and then instrumental analysis. The analytical sequence of trace samples involves a physical description of the atom, followed by the sample collection and instrumental analysis directly. The trace samples are analyzed while using all of the precautions required to prevent the contamination of the material. The laboratory, equipments, chemicals, and operators must be free of cannabis and should be tested prior to sampling of the casework materials. The bulk samples come in a large variety of sizes. If they are wrapped, consideration should be given to preservation of the wrapping, because this might allow the links between samples to be established and the fingerprints to be recovered. The material should be taken from the bulk of the drug, not from the outer layer. A good physical description of the atoms, in particular bulk samples of the cannabis, should include the size, weight, color, smell, shape, and physical relationship of each sample. The qualitative identification of the cannabis involve the identification of the potent or responsible phytochemicals, and the identification of the herbal material. The method used to identify cannabis products depend upon the nature of the products which are to be identified. The herbal materials can be identified on the basis of its morphological characteristics, while in case of resins and harsh oil, the identification is made on the basis of phytochemical identification and the proof of the presence of delta 9 THC, its precursors, cannabidiol, and its breakdown product, cannabinol. These are the structures of the three phytochemicals which are identified during the analysis: delta 9 THC, delta 9 CBD, that is cannabidiol, and delta 9 CBN, that is cannabinol. If the samples which are obtained are the herbal material, they can be identified for the possibility of cannabis sativa. Botanically, cannabis sativa can be identified on the basis of its gross morphological features and, more importantly, by the presence of microscopic structures on the surface of the plant. And these microscopic structures are named as trichomes. At the macromorphological level, it has a square stem with four corners and has a palmate leaves with serrated edges. Microscopically, there are three types of trichomes are observed, namely glandular trichomes, unicellular trichomes, and cystolytic trichomes. And the structures of these trichomes are shown in this figure. The first one is the glandular trichomes, the middle one is unicellular trichomes, and the last image is for cystolytic trichomes. The glandular trichomes are the structures in which the cannabis resin is produced, whereas the unicellular trichomes are found all over the plant but only point up to the plant, whereas the cystolytic trichomes are found all over the plant and may have oxalic acid crystals visible within their bases. If all of these three trichomes are found together, then the plant material can definitely identified as cannabis sativa, since no other plants display such combination. The presence of these trichomes will confirm that the herbal material which is obtained is a cannabis sativa plant. The other materials can also be identified, and the identification is mainly based on the identifying three phytochemicals named as THC, CBD, and CBN. If the morphological characteristics of the cannabis sativa are not all present, or if they have been destroyed, for example, in resinous material or material that has been smoked, it is necessary to identify the material through its phytochemical content. And this identification involves the identification of three principal phytochemicals: delta 9 THC, delta 9 CBD, and delta 9 CBA. For bulk samples, the analysis follows the sequence presumptive tests, TLC, and then identification by GCMS. Whereas if the sample is a trace samples, then they are analyzed directly by using the GCMS. Two tests are generally used as the presumptive tests for cannabis. The first test is called Dequinoise Levine test, and the second is the Corinth 4 salt test. And both tests involve a reaction between the cannabinoids and a test reagent to form colored products. Positive and negative control tests should also be carried out along with the sample. The first test involves three reagents. The first reagent is a mixture of 2.5 ml of acetaldehyde and 2 gram of vanillin in 100 ml of 95% ethanol. Second reagent is concentrated HCl, and the third reagent is chloroform. In a test tube, we have to add 5 drops of the first reagent and then the material to be tested, which has previously had a drop of ethanol on it, is added, and in order to solubilize the cannabinoids, the ethanol can be increased. The mixture should be shaken, then 5 drops of HCl are added, and the mixture is shaken again. 10 drops of chloroform added, and again the mixture is shaken. Two phases are then allowed to separate. If the cannabinoids are present, they rapidly form a blue or purple color, which will be extracted into the chloroform layer. And absence of this blue color to the chloroform layer indicates absence of cannabinoids. The second test is called Corinth 4 salt test, and the material to be tested is placed on a filter paper and a second filter paper is placed on the top. A few drops of diethyl ether are placed on the top paper above the material to be tested, and the paper is squeezed into the material to mop up the ether extract. The top paper is removed and the ether is allowed to dry. A small quantity of Corinth 4 salt in anhydrous sodium sulfate is placed on the paper between the edge of the latter and the dried extract. Water is then gently dropped onto the outside of the paper and allowed to move through the paper. When the water reaches to the Corinth 4 salt, it dissolves this reagent and thus carries it towards the dried cannabis extract. When the Corinth 4 solution reaches the cannabinoids, pink and orange products are formed, thus indicating the possible presence of cannabis. The cannabinoids are readily oxidized and so should be prepared for TLC in a solvent in which they are stable. As with the swabs for trace samples, ethanol satisfies this criterion at this stage. The samples should be prepared by suspension in ethanol at a concentration which will yield a cannabinoid content roughly the same as for the positive control. The extracts, positive control and a negative control, are spotted onto a silica chromatographic plate and allowed to dry. The most frequently used mobile phase is toluene, although other systems can be used, but toluene is frequently utilized. The chromatogram is developed, removed from the solvent, and the mobile phase allowed to evaporate at room temperature. If toluene is used, drying of the chromatographic plate should be carried out in a fume compartment. Once the plate is dry, the compounds present should be examined visually under the white and the UV light and after spraying with 1% fast blue BB in water. A variety of red, orange, brown and yellow compounds are formed as a result of the reaction of fast blue BB with the cannabinoids. And by comparing the color formed in the sample with the standard. The probable cannabinoid can be identified by this technique. Once the cannabinoids are identified in TLC, they can be further confirmed by using gas chromatography mass spectrometry technique. In order to identify the cannabis products, one of the most frequently used method is GCMS, and the identification relies on the presence of delta 9 THC, CBD, and CBN in the sample, and to a lesser extent, the presence of delta 8 THC, which is the isomer of the active principle of cannabis, and delta 9 tetrahydrocannabinolic acid. The sample can be prepared based on the type of the sample, whether it is a bulk sample or a trace sample. The bulk samples are triturated in ethanol, while the trace samples on the swabs are eluted by using the same solvent. Ethanol is chosen because it satisfies all the requirements of a good solvent prior to further analysis. The standards are also prepared in ethanol in the same concentration range as that of the sample, and an ethanol itself acts as a negative control. The samples are centrifuged to remove any solid material which might block the syringe or the gas chromatographic system, and the supernatant is used for subsequent analysis. The samples, standard and negative controls are placed in GCI vials and blown down under the nitrogen. The residue is usually presented as an oil. The derivatization reagent used in case of cannabinoids is 100 microliter of 10% NO bis trimethylsilyl acetamide in N-hexane, which contains N-dodecane as an internal standard. The derivatizing agent is added to the sample and the sample vial sealed, and it is shaken to allow the derivatization at room temperature. The derivatization takes place as per the reaction shown. The materials are analyzed in the following order: first the derivatized blank, then derivatized standard, followed by derivatized blank, then derivatized negative control, and again derivatized blank, then the derivatized sample, and so on, with a positive control at every fifth or sixth injection. These are the typical requirements for a GCMS instrument for the analysis of cannabinoids. The column is of OB1 or the equivalent type with the length 25 m into 0.22 millimeter inner diameter. The injection temperature is 290 degrees Celsius and column over temperature is 170 degrees Celsius for 2 minutes, which is increased to 280 degrees Celsius at 4 degrees Celsius per minute rate. The carrier gas is helium with a flow rate of 1 ml per minute, and the detector which is used is the mass spectrometric detector with temperature and settings are required. A typical separation which can be achieved and the mass spectra of the trimethylsilyl ethers of the derivatized cannabinoids are shown in these figures, and on the basis of the availability of the retention time data and the mass spectra of these compounds and comparison of these between the compounds in the sample and the standards, and identification can be made.